So the first bit of chemistry here is going to be kind of structure of the atom, a little bit of history, okay, things like that, and then we'll get into naming compounds and stuff like that after. So today, and maybe a little bit of tomorrow, is going to be history and structure of the atom. So we're going to look at how the theories of the structure of the atom were developed, okay, and basically why our idea of what the atom looked like changed, okay, and then obviously the parts of the atom and their characteristics, which hopefully is review, okay. What's an atom made out of? What would be the three things that I'd find in an atom?
A proton.
Protons?
Electrons.
Electrons? And neutrons. Okay, protons, neutrons, and electrons. That's the three parts of the atom. Okay, what you're going to need to know basically is, according to our current model of the atom, where would I find those things and how many of them would there be in a particular atom? Okay, like that's kind of the end game here that we're looking for. All right, so chemistry goes back a long way, okay? But not so much that it was always chemistry. This is more like the ancestor of chemistry, and that would be alchemy. Okay? And even before alchemy, there was this idea of what matter was built out of and things like that. But we'll talk a bit about alchemy and the birth of chemistry here. So we've used chemistry for a very long time without really understanding why or how what we did worked. Just that it worked. That's kind of the history of mankind. It's like, hey, look, this works. Doesn't matter how or why, it just does. I mean, when we pick up and use our phone, we don't necessarily understand how every little bit and piece of that phone works, but we know it does work and we know it does a job. Okay, and so we've used that for a long time to dye cloth, to cure meats, to preserve things, or to create energy or release energy, okay, things like that. So we didn't always know why it happened, but we knew that it did happen and we could use it. Okay, so if we go back quite a ways, okay, the history of the idea of matter goes back to the Greeks, as many scientific things do. Okay? And the Greeks believed that matter was made out of four things: earth, air, fire, and water, the four elements. Okay? Now, when we look at that kind of at the surface, it's like, well, that's pretty simplistic and pretty dumb. Like, obviously, that's not the case. But they had very good reason for thinking that. And they even had a periodic table of sorts that would tell them this stuff is made up of this much water, this much earth, and this much air. All right? Like, for example, steam was some parts water, some parts fire, and some parts air, because that's the three things you combined in order to get it. Okay? You would put a fire underneath the water, okay? The water would boil and it would become air. Okay, so the some parts of those three things. Okay, whereas mercury, okay, which is that silvery liquid metal, right? That was some parts earth and some parts water, because it was obviously not water, but it behaved like a liquid, so it made sense that it would be some parts of each. Okay, it was a very logical conclusion for them to draw that they understood. Because remember, lots of Greeks were not literate. Okay, at that time, like not all of them could read or understand things, so they had these people called thinkers who explained things to them. Okay? And in ancient Greece, if you were a thinker, that was like the best job you could get. All right? Because basically you got to sit in the Acropolis and someone would like fan you with a big palm branch and feed you grapes, and you just had to come up with ideas and explain stuff. Okay? It was a pretty sweet gig, okay, when it came right down to it. So one of the most important thinkers was obviously like Aristotle, Plato, okay, people like that. They were the great kind of Greek philosophers. Okay? But there was also this guy named Democritus. And Democritus, one particular day, decided that this whole earth, air, fire, and water thing maybe didn't make as much sense as everyone thought. And that all matter was actually made of these tiny particles that you couldn't see. And they were the smallest unit of matter. So he called them atoms, or atomos, which in Greek means uncuttable. Okay, so you couldn't make it any smaller. And when he came up with that idea, people looked at him strangely and said to the guy who was supposed to be keeping him in the shade with the palm branch, "You're not doing your job. This guy's like, he's got sunstroke or something, because that idea doesn't make any sense." Okay? So it was kind of thrown by the wayside, but now obviously we know he was right. Okay? It's just for them, they had a better explanation. Okay? The whole earth, air, fire, and water thing made way more sense, and more respected thinkers like Aristotle and Plato agreed with it. Okay? But we now, of course, know that that's actually the way it is. Now, it wasn't all bad for Democritus. Okay? He did come up with something else that was pretty good. Kind of sounds like his name. Democracy. So he just kind of went into the arts as opposed to the sciences after that, and it worked out well for him. All right. In the Middle Ages, there was lots of experimentation going on with the chemical nature of matter. It wasn't chemistry, because chemistry is a true science that involves sharing of ideas and proper scientific method and things like that. But there was a lot of alchemy going on. Like Leonardo da Vinci would have also been like an alchemist. Okay, this was his lab. Okay, so an alchemist's lab would look like what you would picture, a wizard's lair kind of looking like. It'd be lots of fancy glass containers and beakers and all kinds of mortars and pestles and stuff. Okay, and what they were doing was just trying to basically get rich. Okay, they were trying to find that magic reaction that would get them something for nothing, turn lead into gold, make the elixir of eternal life, and things like that. So they weren't very successful. Okay? Lots of people died trying the elixir of life. Okay? And lots of alchemists probably blew themselves up with their experiments. Okay? But they did learn a lot about how matter behaved, okay, as a result of their kind of trial and error, random kind of experiments. The thing that was kind of bad about alchemy was they were very secretive about what they were doing. So science didn't progress very much because they would hide all of their observations and discoveries from each other. Now, fast forward a few hundred years more, and you get these two guys here, Roger Bacon and Antoine Lavoisier. They're considered to be the fathers of the scientific method. Okay? They're the ones that took alchemy and turned it into something legitimate. Okay, by introducing the scientific method, which would mean you have a problem. You devise an experiment with variables. You come up with a hypothesis. Okay? You test that hypothesis with a controlled experiment. Okay? You record observations. You analyze your data. You come up with a conclusion, and then you communicate that, and you have your peers review it and try and replicate it. Okay? That's the process by which all real science is accomplished. Okay? There has to be this communication and replication by others in order to prove something to be valid. Okay? And that's what was missing from alchemy. So that kind of took alchemy and turned it into a real science, where then suddenly everyone was finding out that matter has patterns of behavior. Okay? And from those patterns of behavior and those experiments, we could determine what the structure of matter was. Okay? At least at various levels, okay? As our understandings improved. Okay, so the idea of the atom is this. It's like Democritus said. It's the smallest unit of matter that retains the properties of that material. So if I had like a chunk of iron or lead or something like that, and I kept cutting it into smaller and smaller pieces, would all of the smaller pieces still have the same properties as the big piece? I mean, other than size. Right? They still all have the same melting point, the same boiling point, okay? The same density, all of that, because it's still that same material. And if I keep cutting it smaller and smaller and smaller, okay, eventually I would get down to the point where I'd have a single atom of that lead. Now, I could never actually physically cut it that small, but let's say we could. Okay? That single atom would still have all the same properties as all the other chunks of that material. It's the smallest unit of that material. If I go any smaller than that, then I'm splitting the atom. Okay? And at that point, I am changing it. It is no longer an atom of lead, now it's something else. Okay? That's nuclear fission. And fortunately for us, you can't do that while chopping carrots, okay, in the kitchen. Okay? Because your knife edge is millions of atoms wide. Okay? So you never have to worry about splitting the atom while cutting things with a knife. Okay? It's just not going to happen. All right, does that sort of make sense to everybody? So the atom is this smallest unit, okay, of matter that still retains the properties of that material. Okay, so that stuff there that's in bold, okay, that's important. Okay? Now, the atoms, obviously, of different elements look different. That's why they have different properties. Okay? An atom of lead, for example, okay, has 82 protons in it. It's a very large atom. That's why lead is very heavy. Okay? Whereas an atom of carbon has only 6 protons in it. It's a much smaller atom. Okay? Carbon is much lighter. Graphite is carbon. Okay? It's one of the nice light structural materials that we build things out of. Okay? But it's much, much lighter because the atoms are much, much smaller. Okay? Their structure is different, and so carbon and lead have very different physical and chemical properties. Okay? Carbon, like we said, is a lightweight, kind of non-metallic material, okay, that can be either graphite or diamond or any of those things, whereas lead is a very heavy metal. Okay? Very different, looks very different, feels very different, behaves very different. Okay. Don't be afraid to ask questions as we go here, guys, if you got them. All right, so in the 1700s, after Bacon and Lavoisier have brought in the scientific method, these patterns of behavior of matter are starting to become evident. People are seeing certain things happen. And they're communicating their results, and they're saying, okay, what is this going to tell us about the structure of matter? Okay? And so an English chemist named John Dalton took these experiments, and he said, okay, this is what it says about the structure of matter. First off, it says, all elements are composed of tiny, indivisible particles called atoms, because they could see that when they reacted things together, changes occurred that could only be explained by particles of things moving around. The four-element idea didn't explain how a chemical reaction occurred. Okay? And so they had to come up with something else, and that was back to Democritus, that everything is made of these particles. Okay? Further to that, atoms of the same element are identical. So if I have a big lump of carbon, every single atom in that lump of carbon is the same. They're all carbon atoms. They all have 6 protons. They all have 6 electrons. Okay? They all have 6 neutrons. Right? They're all identical. Now, we know that to be mostly true. There's some exceptions to that. Okay? But we still hold this as the second point. Okay? The third point says that atoms of different elements can combine with one another in simple whole number ratios to form compounds. And this part is important. Whole number ratios. That part's important. It means you never have half an atom in a reaction. Okay? And what I mean by that is this. This is water. Do you see any fractions in it? Like I would never write water like this. Okay, that says I have half an oxygen atom. Well, half an oxygen atom is only 4 protons. That means it's not oxygen, it's beryllium. Okay, so it's always whole number ratios. You don't destroy or alter or split atoms in a chemical reaction. In a nuclear reaction, yes you do, but not in a chemical reaction. Okay, and then the last thing was John Dalton's like death blow for alchemy. Okay, alchemists thought there was a way to turn lead into gold. Okay, to turn cheap stuff into valuable stuff. Okay, and they thought that for good reason. When they mixed things together, they noticed that what they got after was different than what they started with. So they just figured there has to be a way to turn this thing into that thing. As long as I mix it with the right stuff, that'll happen. What they didn't understand was the structure of matter. Okay? That gold is an element. I can't mix 2 things together to form an element. They were forming compounds. They just didn't know that. Okay? So that's why it was reasonable for them to think, I can do this. We know now, obviously, that's impossible. And that's what Dalton's 4th point of his atomic theory put the end to. Okay? So chemical reactions occur when atoms are separated, joined, or rearranged. Okay? However, atoms of one element are not changed into atoms of another by a chemical reaction. Okay? So I can't turn lead into gold. Right? So the reason that Dalton knew this was in all the experiments that had been performed, new elements were never produced. So he could have had, let's say, something like this. Okay? That would be the chemical reaction that would form water from hydrogen and oxygen. Did I make any new elements? I started with hydrogen and oxygen, and I ended up with water, which is made of hydrogen and oxygen. I didn't make any new elements. Okay? So this would be an example of atoms being joined. Okay? Atoms could also be separated. Okay? We could have something like this. Okay? I start with sodium chloride and it splits, it separates. Well, I still end up with sodium and chlorine. I didn't make any new elements, but I separated some atoms. Okay? Or I could have a reaction where atoms get rearranged. I could have something like this. Okay? In that case, I've rearranged the atoms, but I still have all the same atoms I started with. I didn't make anything new. Right? I'm never going to have a chemical reaction where this happens. Okay? That's what the alchemists were trying to do. They were trying to take cheap stuff like magnesium and oxygen and turn it into gold. I can't do that. Okay? That's making a new element. I can't make a new element. I can only have the elements that I had to begin with. Okay? So that's what Dalton's fourth point said could not happen. Okay, how important do you suppose the 4 points of the atomic theory are? Could they be on your quiz on Thursday? Definitely. Okay, definitely know the 4 points of Dalton's atomic theory. Okay, they form the basis for what we know about the behavior of all matter. Okay, and so thus they are very important. Okay, all matter is made of tiny particles called atoms. Okay, and those particles are indivisible, not invisible, indivisible. Like, yes, we also can't see them, but that doesn't mean they're invisible. Okay, they're not, we can't split them in a chemical reaction. You can split them in a nuclear reaction. Okay? Atoms of the same element are identical, okay, and the atoms of one element are different from those of another element. So atoms of the same element the same, atoms of different elements are different. Okay? Atoms can combine in whole number ratios to form compounds. And fourth point, what happens in a reaction? Atoms can be separated, joined, or rearranged, but not turned into other atoms. Okay? All right, questions on Dalton's atomic theory? Okay. So, Dalton's atomic theory was a big deal. In fact, it was very unifying in terms of getting like chemists working together and learning a lot and experimenting a lot. But the natural question for Dalton after he came up with this was, okay, that's great. What do atoms look like? And Dalton didn't really have an answer for that. It was kind of like, see my first point about them being tiny? I don't know what they look like. They're tiny. I can't see them. They're too small. People are like, I don't really like that answer. I mean, that's fair. Okay? We want to know what they look like, how they behave. So since there wasn't anything to say this was wrong, Dalton said, okay, they're tiny little spheres. I mean, a sphere is a naturally occurring shape, right? Planets and stars and all kinds, they're all sphere shaped. So atoms are spheres. Okay? And it made sense. all the behaviors he had observed could be accounted for by having, you know, a ball of this and a ball of that joined together or split apart. It fit. We didn't know about protons, neutrons, or electrons at this point. So it made sense to say an atom is a tiny sphere. Okay? Now, each sphere is different. A sphere of carbon is different from a sphere of lead. Okay? But that's what we knew at the time. Okay? So that was the first model of the atom, Dalton's solid sphere. Okay? Now, it didn't last very long. And it didn't last very long because a lot of experiments were going on that were showing the behavior and the structure of matter. Okay? One of those experiments in particular was by a guy named J.J. Thomson. Thomson was doing experiments with what was called electrochemistry. So his experiments were chemical reactions that would produce electric currents, basically the things that allowed us to build batteries, okay, eventually. Now, when he started these experiments and he started getting electrical currents being produced, Dalton's model couldn't explain where the electricity came from. Okay? Because we know that electricity is the flow of electrons through a wire. Okay? There was nothing to explain how a chemical reaction could make stuff travel through a wire and turn on a light, okay, or power a fan or do something like that. Right? So there had to be some other part of the atom that the solid sphere hadn't accounted for. Right? So J.J. Thomson was, you know, he was respectful of all the work that Dalton had done, so he didn't completely destroy the solid sphere, he just added to it. And he said, okay, an atom is still a sphere, but loosely attached to the surface are these small negatively charged particles called electrons, because they make electricity. Okay? So it's a logical thing to call it. And the sphere is positively charged, which is why all atoms are neutral. So we got these negative charges and we got this big positive charge, and when a reaction happens, the reaction can cause the electrons to be shaken loose. And when they're shaken loose, then they can travel through a wire and voila, electricity. Okay? And everyone's like, okay, made sense. There was nothing to say that was wrong, so it explained his experiments. So what they did is they said, okay, Dalton's model can't explain this experiment. This model does. Now, atoms are the plum pudding model. Okay, that's what he called it, plum pudding, because I guess it looked like putting plums in it. Okay, so it fit, and that's what people went with. But again, there's lots of experimentation going on, lots of experiments being run, lots of discoveries being made, and pretty soon it's like electrons aren't the only particle. Okay, there's also protons, there's also neutrons. Okay, all these experiments were going on with the structure of the atom and the different parts. After this, like, chemistry kind of went haywire. Okay, because it was like, well, it looks like this, it looks like that, it looks like this, and nobody had anything or any experiments that could prove one model over another, so there was actually a lot of division, okay, for a number of years about what does the atom look like. All of these things could be what the atom looked like, but we can't prove any one of them. Okay, so some people said, yeah, it looks like this, it's still the plum pudding, but there's a solid mass, and then there's neutral things, and positive things, and negative things, and they're all stuck on it. Okay? Or there's protons and neutrons, and then there's electrons. I mean, this is a little closer to what we know it looks like, but it wasn't totally accurate either. Okay? So that kind of, like I say, threw a monkey wrench into things because we were discovering these other particles, but really had no way to know how they were arranged together. Okay, and then Chadwick discovered the neutron. Okay, so yeah, we got protons, we got neutrons. Okay, so what happened later is this guy named Ernest Rutherford decided he needed to prove what the atom looked like, and he came up with a really ingenious experiment to do it. He was one of the people who believed in the nuclear model of the atom. That is, that the atom has a central dense nucleus made of protons and neutrons, and then the electrons orbit. Okay? Because orbits are a very natural phenomenon. Okay? They're orbits due to gravity. Well, electrons orbit because opposites attract. The nucleus is positive, the electrons are negative. There's an attractive force like gravity attracts, you know, the Earth to the sun. Well, electrons are attracted to the nucleus because they're negative and it's positive. So he's like, I'm going to prove that that there's a nucleus. What he was wrong about was how big the nucleus was. Okay? He kind of misjudged what the size would be. So he developed this experiment where he took a piece of gold foil, okay, so he took this piece of gold foil and he put it in front of essentially like an X-ray machine. Okay, so he put this gold foil in front of the X-ray machine and he said, all right, this gold foil is really, really thin. So imagine it's like tin foil, okay, but it's made out of gold, but it's much thinner than tin foil. It would be more like a Kleenex, but maybe even like thinner than that. Like it's only a couple of atoms thick, okay? And he's gonna fire this beam of beta particles, or alpha particles at it, X-rays basically, and if there's a nuclear model to the atom, then some of the beams will get through because there'll be spaces between the atoms, okay? And the X-rays are small enough that they would fit in between, okay? And some would get deflected, okay? His prediction was that basically all of it was just going to get through, okay? Because he believed the nucleus was much smaller than it actually is. Okay? So when he fired this thing up, he was actually quite surprised by what happened. Because yes, he got a bunch, so he surrounded this whole apparatus with photographic film. I know this is a bit of a generation gap for you guys because you probably never used a camera that actually had film in it. But back in the day, cameras had film in them, and if you exposed it to light, it would change from like brown to white. Okay, and obviously color stuff worked a little differently. Okay, so what happened here is he put this photographic film around and then he fired up the X-ray machine. And anywhere where the X-rays hit the film, there'd be a bright spot or an exposure. There was a whole bunch of exposure behind. Lots of the X-rays got through. But surprisingly, there were spots everywhere. Okay? Not as many as on the back, but there were spots deflected, there were spots behind it. Okay? And the only way that those rays could have gotten there is if they hit an atom and bounced off of it. Okay? So what Rutherford interpreted those results to mean was that yes, some of the beams, they went straight through and they exposed the camera film behind. Okay? But some would hit the nucleus of an atom and be deflected. Some would get deflected so much that they almost bounced straight back at the emitter. Okay? And so that was the part that surprised him. In fact, he was so surprised, he's like, it was like shooting an artillery shell at a piece of paper and having it bounce back. Okay? That's how surprised he was by how many things actually hit atoms. So the nucleus was actually a lot bigger than he had predicted it to be. All right, so Rutherford's experiment with the gold foil, definitely know that. It's like the most important experiment that was run in terms of structure of the atom because it proved that an atom has a nucleus. Okay? And in that nucleus are the protons and the neutrons. Okay? Before this experiment, that wasn't known for sure. Okay? So Rutherford's gold foil experiment proved the existence of the nucleus. Okay? Now, here's where it went bad for Rutherford. He proved the existence of the nucleus and then totally messed up what the electrons do. Okay? Because his model looked like this. Okay? This is what he said all atoms look like. The nucleus is in the middle, and the electrons all orbit at equal distances. They're just offset. So their orbits are just offset a couple of degrees, which doesn't really work for a lot of reasons, but mainly because as an atom gets bigger and bigger and has more and more electrons, they would have to run into each other, okay? Or at least get close enough that because they're both negative, they would repel each other and cause weird things to happen, okay? So this model didn't hold up for very long. The idea of the nucleus was fine, but his arrangement of the electrons was really bad. Okay, so it didn't last long. So what ended up happening was Bohr came along and he determined that electrons actually have different energy levels. Their orbits are more like planets, with some of them being further away. Okay? And the ones being further away had more energy because they would have to move faster and things like that. Okay, so the Bohr model is kind of accepted still, not really, but kind of. Like if we took a picture of an atom, it might look like Bohr's model because we would freeze the electrons in position. Okay? And then it would look like, okay, yeah, there's some electrons here and there's some electrons here. Okay? But what we know is that an atom is not frozen in time. An atom is always changing. And the electrons are always moving, not just orbiting, but jumping up and down, okay, based on how much energy they have. Right? This was something Bohr didn't know when he came up with his model. Okay? So after Bohr came a guy named de Broglie. Okay? And de Broglie was doing experiments with fluorescence and kind of a little bit with photosynthesis. And what he knew happened was some molecules, like fluorescent ones or like chlorophyll, when energy, especially light, would hit them, they would gain energy. And the electrons would move really, really fast, and then they would jump. They would move away from the nucleus. And then as soon as you removed that energy, the light energy in particular, they would slow down and fall. And when they fell, they would release the energy they had gained. For fluorescent materials, that means that they would temporarily glow in the dark. I don't know if you guys have ever seen this, but some things, if you have them in the sun and then you put them in the dark, they glow for a short period of time. Okay? That's caused by the fact that electrons can gain energy when they're here, and if they get moving fast enough, they'll leap to a higher energy level. But they'll only stay there as long as the energy is sufficient to keep them there. As soon as the energy is gone, they slow down and they fall back down. And when they fall down, they release the energy that made them jump up. Okay? And if they release it as light, that means they glow in the dark. For a plant, for chlorophyll, this is how they carry out photosynthesis. When the electrons fall back down, the energy they release is used to make sugar. Okay? So that's how they convert the solar energy into chemical energy in sugar, is that the electrons moving up and down give them the energy to break up water and carbon dioxide and put them back together as glucose. All right, so that means then that our currently accepted model of the atom is de Broglie's electron cloud. Okay? Now, the electron cloud sounds like really random, like electrons are everywhere, but they're really not. Okay? Electrons can be found in places called orbitals, and those orbitals are based on their energy level. We don't worry about orbitals or electron configurations in Science 10. It's the first thing you do in Chem 20. Okay, so the key feature of de Broglie's model was that it explained things like fluorescence and how photosynthesis works and stuff like that. Bohr's model couldn't explain that. Rutherford's model certainly couldn't explain it. Okay, that's what makes his model better. Okay, that's what we call the electron cloud or the quantum model, because it accounts for these quantum leaps that electrons can make. All right, so here's what you'd be expected to do with what we've done here on a test. Know the 4 points of the atomic theory. Okay? Know some of the models, okay? Especially the gold foil experiment. And finally, if I asked you, draw me a picture of an atom of beryllium, that you'd be able to do it. Okay? Now, what I would expect in that picture is the cloud model with the right number of protons, neutrons, and electrons, and all of them in the right place. Okay, so let's just walk through what that would look like. Okay, so if I ask you, draw me a picture of beryllium, okay, I would say, all right, where are my protons going? Where do the protons go? I'm sure somebody knows. What part of the atom are the protons in? In the middle, which starts with N, it's the nucleus. Okay, how many are there? Yep, 4. Okay, on your periodic table, the atomic number tells you the number of protons. Okay, now it also tells you the number of electrons, because all atoms are electrically neutral. They have the same number of protons and electrons. Okay, so that number tells me both. It does not tell me the number of neutrons. Okay, to calculate the number of neutrons, I've got to use this number and this number. What do I do with them? Anybody remember from Science 9? I subtract them. Okay, this is the atomic mass. Okay, so it's the sum total of electrons, protons, and neutrons in an atom. Electrons are so small that they basically don't account for any part of this. So when I go 9.01 minus 4, I get 5.01. Can I have 0.01 neutrons? So how many do I have? 5. Okay, so I just go this minus that, and I got the number of neutrons. So now what I would do is go, all right, in the nucleus, there are 9 particles. So I would draw 9 circles, and I would make 4 of them protons, 5 of them neutrons, and then where do I put the electrons? Around it, yeah. Got an electron cloud picture of an atom of beryllium. It's got 4 electrons in the cloud. It's got 4 protons in the nucleus and 5 neutrons in the nucleus. Okay? That'd be a 5-mark question on the unit exam. Okay? You get 1 mark for having a cloud model. Okay? You get 1 mark for having everything in the right place. A mark for the right number of neutrons, a mark for the right number of protons, a mark for the right number of electrons. 5 marks. Pretty easy 5 marks? Remember that I said that could be a unit exam question. Spoiler alert, that's a unit exam question. I'm telling you right now. Okay. This making sense to everybody so far? All right, so according to our current understanding, the atom is a cloud of electrons surrounding a dense nucleus containing protons and neutrons. Okay, we know that because there's lots of experiments that have told us this is the behavior of matter. Okay, this is where everything is located. The gold foil experiment, okay, the behavior of fluorescent materials, all of that all supports this. Do we know 100% for sure that this is what an atom looks like? No. This is what we can assume from the data that we have. In the same way that all Dalton could assume was that it was a solid sphere. Okay, we do the best with what we know. Okay. All right, so if we're actually truly looking at what an atom would look like, okay, these are the orbitals I was telling you about. Okay, electrons are, yes, in a cloud, and they're kind of everywhere, and they can move around, but these are the areas where I'm most likely to find them. Okay, and they're based on energy. The closest ones would have the least energy, okay, and then you could find them in other places depending on how much energy they have. And this is only some of them. Okay, they get like even weirder looking, okay, as you go along. That doesn't show them all. I think there's one that's even shaped like a donut that goes around the middle, and yeah, just weird stuff. Okay, but you don't have to worry about those until you get to Chem 20. Okay, for us, we're just going to say they're in a cloud. They're happy there. Sorry guys, my computer's starting to lag. Okay, on the first page of your chemistry worksheet booklets, okay, so if you bring up that file, okay, the chemistry worksheet booklet, are some questions that I would like you to answer from these notes. Okay, I'll put the first few on the board here in case you can't access that right now, okay, and that's what I would like you working on for the remainder of class here today. Okay, I'll give you a little bit more time tomorrow in class to get them done so they're not homework. Okay, and then we'll go through them as a class after that, and then we'll get into naming compounds from there. Okay, so if you're working on those, some good like complete sentence answers, because this is the kind of stuff that will be on your quiz on Thursday. Okay, could be multiple choice items on a unit exam. Okay, things like that.